Swayam Prabha. Digital India. Educated India.
Today we are going to look at modeling of positive feedback systems in detail and the underlying behavior. So, the positive feedback system or a reinforcing type of system, the variable will continue to feedback onto itself and will reinforce its own growth or collapse. Examples would be the arms race. You can see the threat perceived by nation B will drive the weapons of nation B, which then affects the threat perceived by nation A, which then drives up the weapons of nation A. So, this entire loop is a positive feedback system which continuously reinforces itself and which in popular literature is also known as the arms race. Or a more simpler example could be the population growth, where if the net birth rate is positive, then we expect the population to grow. So, here the population will not grow linearly, because whenever there is more births, it increases the population, and after some time that increased population will contribute to further increase to the higher birth rates, right. So, this is going to continuously feed itself and will result in a exponential growth of the variable population. So, the characteristic behavior, I think we saw it last time also, it is an exponential growth, but to get a more realistic feel of what is it that we are looking at, because it is not perceivable in the short run, we need to give it some time. So, consider a paper, thickness 0.1 mm, we fold it in half, then we again fold it, how thick will it be? It should be 0.4 mm, right. When you fold it in half, it becomes 0.2, then we fold it again, then it becomes 0.4. So, with every fold, it doubles right there. How thick will it be if we fold it 42 times or 100 times? Imagine the paper is big enough. Any ordinary piece of paper, probably not more than 7 times you can actually fold it. But imagine if you can actually end up doing it just 42 times, we are just 2 times, 3 times, it's not a really infinite number of times you are folding it, it's countably finite number of 42 times. If you do the math, that is more than 400,000 kilometers. Kilometers, you just change the units from millimeters to kilometers, 400,000, which is more than distance from here to the moon. So, that is how big an exponential can grow without, if it is left unchecked. So, this exponential growth that we just saw characterizes most of the positive feedback systems. The other one is characterized by accelerated decay or exponential decay. So, with time, initially when it seems like systems is going fine, but after some time you can find that there is an exponential growth that has occurred. So, positive feedback or reinforcing systems. What we are looking at is net flow rate affecting your stock. So, this is a positive feedback loop or a reinforcing loop. L plus or R can denote it. The characteristic behavior could be exponential growth What are the variable of interest? Let us assume it is a stock. So, this is your exponential growth. Other part is accelerated decay. Or exponential collapse. X-axis is always time. How will the shape of this be? Accelerated decay or exponential collapse. We have how many options do we want to? Is it going to be this way? Or okay, of course, this is growth. What other options we have? It's going to be this way. This is an accelerated collapse. Since very less quantity seems to get down, this doesn't increase, it's actually flat. It's part of the diagram, but after some time, it just after crossing point, it just starts collapsing faster and faster before it hits 0. The example I illustrated was panic selling in stock markets or panic buying, not panic buying, panic selling. Nobody buys in panic. Why people sell in panic? Panic selling or withdrawing cash from the banks. Just a message that the bank is running dry of cash is enough for people to start queuing up. Initially, they get less and less amount, then suddenly you are faced with riot scenarios. So that we characterize as a exponential collapse in the system. So there is a what characterizes these two is while system is here or even system is here, it seems that things are all fine, but then if the same amount of time you wait, suddenly the system becomes at unmanageable size. So up to here things are okay, and then you just waited a little longer and the system becomes unmanageable, or here it was fine till here, then you waited a little longer and now system becomes unmanageable size, which is here, which you didn't want. So that is a characteristic behavior of exponential systems where things seems to be okay, but the growth is being unchecked within the system. Now to model this as a stock flow diagram, let us see how we are going to go about doing that. Let us see, look at the SFD representation or model. There is a stock, so it is a rectangle, and there is a net flow rate, net flow or net inflow. And we see that the stock again feeds back into your net flow rate. So, I have to represent that with a positive sign. So, the top causal link is represented by this thick arrow with a valve. The bottom causal link is represented by an explicit causal link in your stock flow diagram. And to now capture the relation between the net inflow versus stock, let us introduce a new variable called as fractional growth rate. Let us have this as G, let us define the stock as just a variable S for simplicity. So, the underlying equations here, since stock would be given as change in stock or dt is nothing but net inflow, that is ds by dt. My net inflow, let me just simply define as G multiplied by stock S. As I told, G is the fractional growth rate. So, units can be fraction per time. The stock units are just simply units. Net inflow rate becomes just units per time. So, this the simple equation that is underlying this diagram that we just drawn here, the stock is just ds by dt, and fractional growth. The net inflow rate is nothing but g into s. So, at every point in time, I am adding g into s to the stock values, right. So, if I want to actually simulate, what I want to do is stock at time t plus dt is okay, minus say stock at time t is nothing but dt into net inflow at time t, or stock at t plus time dt is stock at, is a minus sign, stock at time t plus dt into g into s, which is again at time t. So, dt is the time step. If you are still using Euler's method, let us say time step of 1, then dt is simply 1. So, s at time t plus 1 is s at time t plus 1 into g into s of t. And to simulate this model, all we are going to do is keep solving this equation again and again. Right. So, if you want to do it manually, how will we go about doing it? First is say we have to initialize some value of stock. So, actually the behavior depends on the initial value of stock, right. Behavior depends on initial value of stock at t equal to 0, right. Why does it behave? Why does it depend on that? The simple reason is stock value is 0, what will be the behavior? Will be nothing, it will be just the stock value will continue to be 0 forever, because the initial value of stock is 0. So, if it is 0, then we can expect no growth. If it is any value greater than 0, then we can expect exponential growth. The two possible behaviors are there. If it is, again, assume g is greater than 0, as long as g is strictly positive, we are going to get a exponential growth. Of course, stock has to be non-zero for this to kickstart, else system will will exhibit no growth. So, let us use the diagram we just saw, the underlying equations. So, if you want to contextualize it to this very focused example, assume you put money in a bank and it is going to accumulate interest, compounded interest every year for the next say 15 years. So, this simple diagram here represents how the interest accumulates in a bank, and though you may feel that bank is not giving you adequate interest and the money does not seem to grow the speed which you may want it, but actually the growth exhibits a exponential growth. To simulate it, so let us do a quick hand simulation. We typically initialize the time at 0 and initialize stock at the initial value. Then see, first the net flow is calculated based on the current value of stock. Then we add the increment, that is delta t into the net inflow increment time, and then we add this whatever increment we calculated to the stock. So, this time is not reaching end time, we keep looping. This may look unnecessarily confusing, but what we want to do is shown here. So, let us assume for that interest rate example, the initial value of stock is 100, right. So, first at time 0, the level is 100, then at time 0, so up to this is what is given. Time 0 initial value of stock or level is given at 100. So, we calculate the rate, this 15, the value of G is taken as 15, the interest rate is taken as 15%. So, we take 0.15 into 100 which is 15, and let us assume a time step of 1, the dt is equal to 1. So, 15 into 1 is 15. So, the next time period, we increment time period by 1, then level will be 115, 100 plus 15. Then we repeat the same step, 115 into 0.15, 17.25. So, the next period we add 17.25, we add 17.25 to the stock. So, from this I calculate this, then I calculate this, then I add this to here, then from this I calculate this value 17.25, of course calculate the increment and add the increment, oops sorry to that. Fine. So, I can see when you start with 100, with every time unit passing I am adding an increment value equal to interest rate multiplied by that current value of stock. I mean, we are assuming we are not taking the money out. So, let us see what happens when we plot it. So, we started with 115, the value is now 813.75. So, it is easier to visualize, to see this graph. So, this now starts to exhibit a exponential growth. So, this is the principal value, that is the stock value, and the net interest income, which is your net inflow rate, which will also again exhibit this. Nothing, net income is nothing but a constant multiplier of the stock. So, stock exhibits a exponential growth, this is just a fraction of that, it will also exhibit exponential growth offset by the value of G, which in case is 0.15. Let us see, initially I started with 100, and then by the time it reached 200, it was 1, 2, 3, 4, around time period 5 it reached 200. Let us see how long 200 takes to double. From 5 I start 1, 2, 3, 4, again around time period it reaches 400, that is double, and from, as you can see, so after 5 time period passed it doubled from 100 to 100, after another equal interval of same 5 time period passed, the current value of stock is 200 doubled to 400, and the same equivalent amount of say another 5 time units passed, the stock value doubles to 800. So, with a constant, so interesting thing about this exponential system is there is a constant doubling time, that is after constant time unit passes my stock value doubles in value, which is the characteristic of such a exponential system. So, in this particular example it happens to be 5 time period approximately, but we can actually compute this.